Now we are directly moving into the purely resistive circuit. So purely resistive circuit, you can see here a figure. There is a resistance and an AC sinusoidal voltage is being connected to the resistor. V is equal to Vm sin omega t. The voltage across the resistor is represented by VR and the current through the resistor is represented by IR. Our aim is to find what is the voltage equation and what is the current equation. Comparing these two, we will be getting an idea about whether the current is in phase or it is lagging the voltage or it is leading the voltage. Then only we will be going for a further analysis. Okay, so we know that this voltage which is coming across this resistor, okay, then what will be the voltage equation for VR? What is the voltage VR? The voltage across the resistor will be same as the voltage which is coming from the supply, because there are no other elements in between. So V is equal to Vm sin omega t will be the voltage across the resistor. Next we have to find what is the current through the resistor. How can we find the current through the resistor? Just by using Ohm's law. We know that current is equal to voltage by R, but here you have to note that the small letters of I and V, it represents actually the instantaneous value of voltage. Why? Because the sinusoidal waveform is already a instantaneous value. So the current will be also a instantaneous value of current. So how can we represent it? The current is equal to, the same as IR is equal to V. Instead of V, we can represent as Vm sin omega t. So IR is equal to Vm sin omega t by R. Now here you can see that Vm by R is a constant and we can represent it as Im. Okay, so the equation for current becomes IR is equal to Im sin omega t. Now, where Im is equal to Vm by R, which I already mentioned, and for this resistive circuit, you can identify that only opposition for the current is the resistance, or we can say the impedance for this circuit is equal to R. There is only one opposition. For AC circuits, we will be mentioning it as impedance. The opposition for current, AC current, we will be mentioning as impedance. And for this circuit, the impedance value is equal to only the resistance value. So let us go through what will be the voltage and the currents. Now we got the equations for both the voltage and the current in a resistor. VR is equal to Vm sin omega t and IR is equal to Im sin omega t. Just go through that equations. Just like A and B, you just go through the equation. You can see that there is no phase difference between both of them. So the phi value is equal to 0. And how will we represent in the waveform? Both of them are moving together, where current is having a lesser magnitude because of the resistance. Okay. Now let us go through that phasor diagram. Here you can see the phasor diagram. Both of them are on the 0 axis with different magnitude. This one is the current and this one will be the voltage. Okay, now let us go through an animation video of how will be the phasors, how are they rotating actually. So so here you can see the animation video of a phasor. Here you can see it is starting. Okay, the phasors, both of them are rotating together. In a pure resistive circuit, both of them are rotating together. The voltage and the current, both are rotating together. Now I am changing the resistor and you can see the magnitude of the current has been reduced. Okay, now you can see both of them are again rotating together with a different magnitude in the current. So that happens when there is a change in the resistor. So according to the resistance, how it affects the phasor, I wanted to show. Next, I changed the frequency, reduced the frequency, and now again starting the phasors. You can see that now the phasors are rotating in a very slow manner. Okay. Along with that, you can see that the sinusoidal waveform is also changing its instantaneous value. Okay. So this is how it is being done. Now, so next let's go through what about the power in a purely resistive circuit. So power in a circuit, as it is instant, as the voltage and the current are instantaneously changing, we cannot directly say about the power. So first we are going to study about what is instantaneous power. Same as the instantaneous voltage and current, there is an instantaneous power for the circuit. So instantaneous power is equal to instantaneous voltage into instantaneous current, voltage into current. Voltage we know Vm sin omega t, and the current through the resistor is Im sin omega t. So multiplying both, we will be getting as Vm Im sin square omega t. Instead of sin square omega t, I am representing as 1 minus cos 2 omega t divided by 2. Okay, now we are going to find out what is the average power. We studied how to find the average value of a sinusoidal waveform. Similarly, we are going to find what is the average value for this power waveform. So let us draw the power waveform first. Here you can see the voltage waveform, current waveform, and the power waveform means multiplication of both of them. Volt positive value into positive value, it will be another positive value, and here you can see that orange waveform. Here negative value into negative value, voltage into current, you will be getting a positive value, and that is the waveform for the power in the second portion. So here you can see this will be the orange waveform shows the power waveform. Now we are going to find what is the average value of this power. You can see that it is a positive power. We are going to find what is the average value of this power. Otherwise we cannot mention what is the power. So how can we find the average value? We have studied that if there is a waveform obtained, then the average power is equal to integral. From where to where you are going to take the average? We can take either till 0 to pi, or you can take till 2 pi. Both answers will be same. So here I am going to take from 0 to 2 pi. The equation is P d omega t divided by 2 pi time period, where P is the instantaneous power value, which we already just found out the value of instantaneous power. So the instantaneous power equation is average power, once more I am writing, average power is equal to integral 0 to 2 pi small letter p d omega t, where small letter divided by 2 pi, where small letter p represents the instantaneous power, which we already found out. Now by just substituting that instantaneous power, so this is the instantaneous power equation, d omega t divided by 2 pi. Now you can try to integrate by yourself and just check whether your answers are correct. Okay, then P average you will be obtaining like this. Then substituting the limits, you will be getting the equation like this, and at last you will reach at an equation Vm Im by 2. Now we are going to make it some more different. We are going to write this one as Vm by root 2 and Im by root 2. And we have already studied that for a pure sinusoidal waveform, the RMS value of voltage, that is Vrms, is equal to Vm by root 2. Similarly, IRMS is equal to Im by root 2. So by substituting these two, we will be getting as P average is equal to Vrms into IRMS. Or we can just write as V into I, but we have to keep in mind that this voltage and current both are RMS values. Now, what about the power equation now? The answer we obtained is V into I. Instead of voltage, we can just substitute using the Ohm's law, IR. Then you will be getting the expression as P is equal to I square R. So both these equations can be used for finding the average power in the case of a pure resistor. But the thing is, you have to keep in mind that all of these are RMS value except the resistor. The next one is what is meant by power factor. We are not going to study the complete definition of power factor. Now we are just going to study what is power factor. Power factor of a circuit is cosine of the phase difference between the voltage and the current equation. Okay, so you can see that in this case both are in phase and the phase value is 0. So the power factor PF is equal to cos phi, which is equal to cos of 0. Why? Because phi value is equal to 0 here. So cos 0 value is equal to 1. So the power factor is equal to 1 in the case of a pure resistive circuit. So that is written here. Power is always positive value and the power factor will be always 1. So let us just summarize what we studied. The component, if it is a resistor, then the impedance of the circuit, that is Z of the circuit, will be equal to R. Then the phase difference, is there any phase difference? There is no phase difference. They are in phase. Okay, there is no phase difference. Phi is equal to 0 and the power factor will be equal to 1, as well as the total power will be positive value. So that's all for today. Study well. Hope you understood the pure resistive circuit.